The global production of plastics has reached approximately 380 million metric tons annually, yet only a minor fraction is effectively recycled. Conventional waste management strategies, landfilling, incineration, and limited mechanical recycling, are insufficient to mitigate environmental impacts such as microplastic accumulation and greenhouse gas emissions. Chemical upcycling has emerged as a promising strategy to convert plastic waste into higher-value chemicals, fuels, and materials. Unlike conventional pyrolytic recycling, chemical upcycling employs selective catalytic processes, often based on noble metals such as iridium or platinum, to transform polymers under comparatively mild conditions. In this video, we will discuss some of the principles, mechanisms, and catalytic strategies involved in the chemical upcycling of major commodity polymers, with emphasis on polyolefins and polybutadiene. Plastics are indispensable to modern society due to their durability, versatility, and low production cost. However, escalating production volumes have generated substantial waste. In 2019 alone, approximately 353 million metric tons of plastic waste were produced. Globally, around 49% is landfilled, 19% incinerated, with partial energy recovery but CO2 and toxic emissions, and only about 9% conventionally recycled. Persistent plastics in landfills degrade extremely slowly and contribute to terrestrial and aquatic microplastic pollution. Chemical recycling and upcycling technologies offer a potential route toward a circular plastics economy by transforming waste polymers into value-added products rather than simply recovering material or energy. Recycling versus upcycling. Plastic waste can be processed via mechanical recycling, which remanufactures plastics without altering polymer backbones. This approach is most effective for clean industrial scrap but typically results in reduced mechanical properties due to impurities and polymer degradation. Chemical recycling involves partial or complete depolymerization to monomers or oligomers, followed by purification and repolymerization. Hybrid chemo-mechanical methods combine both approaches. Upcycling differs from conventional recycling in that it produces materials or chemicals of higher value than the original polymer or even its constituent monomers. Chemical upcycling integrates polymer deconstruction with reconstruction into value-added compounds. Chemical recycling of heteroatom-containing polymers. Polymers containing heteroatoms, particularly polyesters such as polyethylene terephthalate, PET, are more amenable to chemical recycling due to hydrolyzable ester linkages. Chemical methods, e.g., solvolysis, catalytic depolymerization, and biological approaches, microbial degradation, have been developed to convert PET into valuable chemical building blocks. In contrast, polyolefins lack reactive functional groups, making their depolymerization significantly more challenging. Polyolefins, scale and waste challenge. The dominant commodity polyolefins, polyethylene, PE, polypropylene, PP, poly, vinyl chloride, PVC, and polystyrene, PS, are derived from simple alkenes, ethylene, propylene, vinyl chloride, and styrene. In 2021, P accounted for approximately 27% of global plastic production, PP for approximately 20%, PVC for approximately 13%, PS for approximately 5%. Together, these materials represent roughly two-thirds of total plastic production and waste. Their low cost and widespread short-term use have intensified disposal challenges. Limitations of thermal depolymerization. Uncatalyzed depolymerization of polyolefins is thermodynamically feasible above their sealing temperatures, Tc. However, these temperatures are high. P. 610 degrees Celsius. pp. 466 degrees Celsius. ps. 397 degrees Celsius. pvc. 350 degrees Celsius. Before reaching Tc, polyolefins typically undergo unselective pyrolysis, greater than 500 degrees Celsius, producing complex mixtures of gases, low-grade liquids, and coke. For example, P-pyrolysis yields alkenes that rapidly aromatize. Even if side reactions were suppressed, the process remains highly energy-intensive due to the large heat of polymerization, e.g., 108 kJ per mole for P. PVC preferentially undergoes dehydrochlorination, 250 to 320 degrees Celsius, rather than depolymerization. Consequently, direct thermal recycling of polyolefins is generally inefficient and non-selective. Catalytic upcycling strategies for polyolefins. Chemical upcycling selectively cleaves a limited fraction of C-C bonds, reducing energy demands relative to full depolymerization. 4 principal catalytic strategies have been developed. Hydrogenolysis. Hydrogenolysis involves metal-catalyzed C-C bond cleavage in the presence of H2. It is operationally straightforward and can proceed below 300 degrees Celsius. Products include saturated hydrocarbons suitable for lubricants, waxes, solvents, and fuels, jet fuel, diesel, gasoline, naphtha. However, terminal bond cleavage produces methane, which lacks added value. Additionally, hydrogenolysis relies on energy-intensive H2, typically generated via methane steam reforming. Catalytic cracking and hydrocracking. Thermal pyrolysis proceeds via radical mechanisms at temperatures above 500 degrees Celsius. Catalytic cracking employs acid catalysts at somewhat lower temperatures, greater than 400 degrees Celsius, generating isoalkanes, alkenes, cycloalkanes, and aromatics. Hydrocracking combines acid functionality with hydrogenation, dehydrogenation components under high H2 pressure. It proceeds exothermically at lower temperatures and produces narrower product distributions, primarily isoalkanes. Carbocation intermediates form through protonation of alkenes, hydride abstraction by Lewis acids, heterolytic or protolytic CH cleavage, radical pathways involving reactive oxygen species. Hydrocracking offers improved energy efficiency compared to pyrolysis and has attracted interest for polyolefin upcycling. Tandem metathesis processes. Alkane metathesis, originally termed molecular redistribution, enables the redistribution of alkane chain lengths through tandem dehydrogenation, alkene cross-metathesis, and hydrogenation steps. In polyethylene cross-metathesis, polymer chains react with light alkanes to form intermediate-length hydrocarbons without requiring external H2, although large amounts of light alkane are needed. The process is near thermoneutral and can operate under relatively mild conditions. Selective oxidation. Oxidation is the predominant environmental degradation pathway for polyolefins, ultimately yielding CO2 and H2O, mineralization. Oxidative upcycling, in contrast, aims for controlled functionalization or limited chain cleavage. Mechanisms include alkyl hydroperoxide formation, radical-mediated beta scission, CH functionalization without backbone cleavage. Selective oxidation can produce oxygenated compounds or functionalized polymers. Excess oxidant, however, results in complete combustion, non-upcycling. Post-polymerization functionalization of waste polymers into higher-value materials also qualifies as upcycling. Polybutadiene upcycling. Polybutadiene, PBD, a synthetic rubber containing one double bond per 4 backbone bonds, is particularly amenable to metathesis-based strategies. Ethanolysis produces primarily 1,5-hexadiene, vinyl cyclohexane, allylcyclopentene. Alpha, omega dienes such as 1,5-hexadiene serve as comonomers, precursors for polyalpha olefins, lubricants, intermediates for telechelych polyethylenes, precursors to bifunctional compounds, e.g., diesters for polyesters and polyamides, sources of alpha, omega diols, after reduction, used in polyurethane production. Hydrogenation metathesis sequences enable controlled conversion of high molecular weight PBD into alpha, omega dienes of tunable chain length. Current technology and challenges. The dominant industrial process for recovering value from polyolefins remains thermal cracking to basic chemical feedstocks. Catalytic upcycling aims to provide more selective, energy-efficient, and economically attractive alternatives. Key challenges include high catalyst and process costs, significant energy requirements, dependence on externally produced hydrogen, difficulty activating chemically inert C-C bonds in polymers such as polyethylene. In conclusion, chemical upcycling offers a promising pathway toward a closed-loop circular economy for plastics by transforming waste polymers, including polyolefins and PET, into higher-value chemicals, lubricants, surfactants, and advanced materials. Compared to mechanical recycling, it provides superior product quality and value retention. However, economic viability, energy efficiency, and catalyst development remain critical barriers. Continued advances in catalytic science are expected to play a central role in enabling sustainable and scalable plastic upcycling technologies.